Welcome to a class of topology. Okay, in this video we are going to discuss about closed sets and topological spaces. We know the definition of open sets in topological space, which is when if A is an element in tau, then A is called an open set in the topological space. A is open topological space X tau. That means all the members of tau are actually called the open sets in a topological space. Okay, now we are going to discuss what is closed sets. Suppose A is a subset of a topological space X tau. Then A is closed in X if A is closed in X if a complement, that is X minus A, its complement is open in X. That means its complement is an element in tau. A set is closed in X if X minus A belongs to tau. That is the definition of a closed set. Okay, A is open if A belongs to tau. A is closed if X minus A belongs to tau. This is we have to remember for open sets and closed set in a topological space. We will see some examples. For example, consider indiscrete topological space. Tau I denote the indiscrete topology, and that consists of only two sets, empty set and full set. So here the open sets are empty sets and full set. What are the closed set? Closed sets are the closed sets are the sets which complement belongs to tau I. Look, if A equal to empty set, then what is A complement? A complement is X minus A, that is X minus empty. X minus empty is X, and X is a member in tau I. When complement of a set belongs to tau I, then the set is called closed, which implies A is closed. Now if A equal to capital X, then X minus A will be equal to empty, and empty is a member in tau I. So which implies when complement of a set belongs to tau I, then that set is called closed, then A is closed. So these two sets, empty set and full set, are closed in this topology also. Now, is there any other subset of X which is closed in this topology? If A is any proper subset of capital X, non-empty proper subset of capital X, then what will be X minus A? X minus A will be again a proper non-empty subset of capital X, comma A is non-empty. When A is non-empty, X minus A subset of X is also non-empty subset. Okay, proper. Then X minus A subset of X is in place. It is also non-empty proper subset, and there exists no proper non-empty subsets belongs to tau I. Therefore, since no proper subset of capital X belongs to tau I, therefore this proper non-empty subset cannot be closed in this collection in this tau I. So but there exists no proper non-empty sets in tau I. Therefore, A is not closed. Thus, only closed sets in this topological space is two sets which are empty set and full set, and they are the open sets in this topology also. Okay. And now consider, as an example, you consider discrete space, discrete topological space, discrete space X tau, and I denote the topology as tau D, discrete topology. Okay. Then what are the closed sets here? A set A is a subset of X. Okay. A is closed if its complement is open. That means its complement belongs to Tori. Then what is x minus a? When A is a subset of x, then x minus a is always a subset of x. And we know that discrete topology consists of every subset of capital X, implies x minus a belongs to Tori. Being a subset of capital X, it also belongs to Tori, which implies every subset of capital X is also closed in discrete space X Tori. And in this collection, in this topology, all the subsets are open also. Okay. Now another example, consider real line with the usual topology. This topology is derived from the usual metric. Okay. Then what are the closed sets in this collection? If you take a small a is an element in real line, consider the set singleton A. Capital A equal to singleton set A. Is it an open set? This, if you want to check this is a closed set, we have to consider its complement. So find the complement x minus a. What is the complement? Real line minus singleton A. And this can be written minus infinity to A union A to infinity. We are just removing one element from the whole real line. So it can be written like this. And what is this kinds of interval? These are open intervals. Open intervals are open sets in this topology. Therefore, these two elements are belongs to tau u. And we know that every topology is closed under union. Therefore, its union is also belongs to tau u. So the whole set x minus a belongs to tau u. When the complement of a set belongs to the topology, that set is called closed. So A is a closed set here. We have intervals minus infinity to A and A infinity are belongs to tau u, and every topology is closed under union. So minus infinity A union A infinity is belongs to tau u, which implies this set is nothing but x minus a. So x minus a belongs to tau u, implies A is a closed set. So it is a closed set. What about the interval closed interval AB in this topology? Is it a closed set in real line with the tau u? So what is closed interval AB? Closed interval AB, its complement is R minus closed interval AB. R minus closed interval AB is minus infinity to A union B to infinity, correct? We are removing closed interval AB from the real line. So minus infinity to A, open A, union this will be our set. So this is again union of two intervals, open intervals. It belongs to tau u, implies closed interval AB is a closed set in this topology. Any closed interval AB is a closed set in this topology. Okay. So every finite set is closed in this topology. Let us assume that A is a finite set. Let A be a finite set. Set of n elements in real line. Then we have to prove that this A is a closed set. That means its complement is an element in topology. Okay. Before that, I assume some order of elements of capital A I assume A1, A2, etc. An are the elements in capital A with some increasing order, increasing in order by using the order property of real numbers. That is A1 less than A2 less than etc. less than An. Okay, then we can plot the elements in the real line A1, A2, etc. An. Okay, this is some order of elements in capital A. Then what will be complement of A? That is x minus A. X minus A is R minus A. That means we are removing all these elements, finitely many elements from the real line. So that real line can be written as minus infinity to A1 union A1 union A2 union A2 union A2 comma A3 union etc. An comma infinity. And you can see that all these are open intervals, and all the open intervals are open set with the usual in the usual topology of real line. So that all of these sets are belongs to tau u, and tau u is a topology, it is closed under union, so it belongs to tau u. When complement of a set belongs to the topology, that set is closed, which implies A is closed in the usual topology of real line. Now, what are the Klopen sets in the topology? Klopen sets. A set which is both open and closed are called Klopen sets. A set which is both open and closed are called Klopen sets. Example, in discrete topology, we know that every set is open and every set is closed. So, all the sets are Klopen. In discrete space, in discrete topological space, all subsets are Klopen. All subsets are Klopen. In indiscrete space, we see that in discrete space, we have seen that the only open sets are empty set and full set, and the only closed sets are empty set and full set. Therefore, the Klopen sets are empty set and full set. Empty set and the full set capital X are the Klopen sets. Okay. Now, you consider set, for as an example, you consider set of the form A equal to closed A open B. Is it an open set or closed set in real line? In real line with the usual topology, it is neither an open set nor a closed set. Neither open nor closed set. But if you consider this A as a subset of real line, it can be considered as a topological space too. And consider the subspace. Consider the subspace A with tau u restricted to A. Then in this topological space, this A is an open set with respect to this topology, because every set is open with respect to its topology. So then A is open in the topology of A. In this topology, A is open in this space tau u with restricted A. Okay. And what is x minus A? X minus, here x is the full set A. So A minus A. A minus A equal to empty. Empty also belongs to tau u restricted to A. Implies complement of A, that is A minus A, belongs to tau u, implies A is closed in this topology also. Is closed. So here the set A is both open and closed in the subspace topology. Subspace topology, which implies A is Klopen in the subspace topology. A set which is Klopen in the subspace topology, but it is not, or it can be neither open nor closed in the full space topology. So this is an example for it.